Hello everyone, my name is Xiandong. I come from the National University of Defense Technology in China. I am glad to have this opportunity to attend this conference. The topic of my talk is Evaluation FFT-based algorithms for strategic convolutions on ARMv8 architecture. I would like to divide my talk into 4 parts: introduction, method and implementation, evaluation results, and conclusion. I will first introduce our research briefly. Convolution has been widely applied in various fields of artificial intelligence. However, it is computationally expensive to perform convolution operation. Convolution operation involves 3 variables: input feature maps, kernels, and output feature maps. In BCHW layout, these variables can be written like shown here, and the calculation process of convolution operation is written here in the formula. It is unit stride convolution if the stride size s equals to 1, and stride convolution if s is greater than 1. Here is the comparison of unit stride convolution and stride convolution. Stride convolution is usually used as the first layer of CNNs, and is very helpful to accelerate stride convolutions. The methods for improving the performance of convolution include matrix multiplication algorithm, Winograd fast algorithm, and FFT fast algorithm. However, the first 2 algorithms both have drawbacks. For matrix multiplication algorithm, it often accompanies by the huge memory overhead. For the Winograd algorithm, if sizes of kernels are not small, a certain loss of accuracy may be introduced. Thus, FFT fast algorithm is often the first choice for high-performance implementations of convolution. This expression is calculation process of FFT-based convolution. As kernels are often much smaller than feature maps, the tiling approach is used to minimize the overhead of padding, where alpha beta stands for the location of tile in feature maps. FFT convolution consists of 4 steps: input transformation, kernel transformation, complex matrix multiplication, output transformation. The third step in FFT-based convolution is element-wise complex matrix multiplication. This expression is the calculation process of it. Each element of the element-wise multiplication is labeled as phi and gamma. Compared with the other 2 methods, FFT fast algorithm has lower arithmetic complexities, and the accuracy loss of it is often negligible. Unfortunately, current implementations of FFT fast algorithm only work for unit stride convolutions, not for stride convolution. There is lots of work about studying high-performance implementation of FFT-based convolution algorithm on different platforms. And we choose to accelerate convolution operation on CPU for the following impure factors. CPU is the most feasible platform, and CPU-based deep learning tasks can further amortize their CPU-based investments, and so on. It is necessary to get high performance while carefully match the architectural characteristics of CPUs and those of convolution operation. Related work mainly focus on the following architectures: NVIDIA GPUs, Intel many-core CPUs, and ARMv8 multi-core CPUs. and some works have focused on the acceleration of strategic convolutions, but they all based on vinaigrette algorithm. There is little work about FFT-based fast algorithms and implementation for strategic convolution on ARMv8 architectures. Let's come to the second part of the method and implementation. We use two methods to achieve FFT-based strategic convolution: the arrangement-based method and sampling-based method. For the arrangement-based method, one strategic convolution with stride size S can be converted into S times S new unit strategic convolutions. This figure is illustration of rearranging a strategic convolution into multiple unit strategic convolutions, where the stride size is 2. The elements of kernels, input feature maps, and output feature maps in new unit strategic convolution can be acquired as this formula. In unit strategic convolution, the white elements with value 0 in input feature maps and kernels are the 0 padding elements, while the gray elements which are derived from formula with condition others comes from input feature maps and kernels. And this formula represents the sum of multiple unit strategic convolutions to get dry convolution. For sampling-based method, it consists of 3 steps. The first step is regarding strategic convolution as unit strategic convolution with the same parameters except the stride size. The second is calculating the unit strategic convolution by FFT. The last step is getting results of strategic convolution by sampling the results of the unit strategic convolution. When the stride size is 2, the sampling-based method is shown in the following figure. Besides designing these two methods, we also analyze the arithmetic complexities of these two methods and compare with the DILAT method. The arithmetic complexities of DILAT, the arrangement, and sampling-based methods for strategic convolutions can be obtained from these 3 formulas. And the formulas of the arrangement-based method can be acquired from following calculation. The process of obtaining these complexities can refer to our paper. Here are normalized arithmetic complexities for FFT-based strategic convolution. When kernel size is large, rearrangement can get much lower ACs than sampling. On strategic convolutions with large kernels, both rearrangement and sampling can provide much lower ACs than the DILAT method, and the rearrangement have lower ACs than sampling. As for implementation, we mainly target an ARMv8-based platform, 510 FT 2000 plus 16-core CPU, and use following optimization: combined communication, multi-level blocking, parallel grid nularity optimization, mesh data layout, and NUMA-aware parallelization. In the next part experiment, we will test the impact of NUMA-aware parallelization. To implement the arrangement and sampling, we also use some optimization techniques. Instead of rearranging all input and kernels tensors before all FFT, we rearrange a type before one FFT. Similarly, we sample a type after one FFT, then store back into memory instead of sampling all output tensors after all FFT. NUMA-aware parallelization is mainly used to optimize the performance of complex matrix multiplication. The difference between using and not using NUMA-aware optimization is shown above. NUMA-aware optimization makes convolution more in line with processes architecture and get better performance. The complex matrix multiplications are first distributed on different NUMA nodes according to the distribution of matrices on nodes. And then, all cores of each node process the divided tasks in parallel. At last, vector units in each core are used to finish the tasks. Okay, now we move to the part of evaluation results. Experiments. The specific parameters of the experimental platform are shown in Table 2. The operating system is Qinglin with Linux kernel, and the GCC was used as the default compiler. This figure shows the architecture of our platform. Then we conducted the test to compare the performance of using and not using NUMA optimization. For convolutional layers, we choose the parameters commonly used in convolutional layers. The specific parameter configuration can be found in our paper. For the arrangement, we can get maximum speed at 2.11 times by using NUMA optimization, and the maximum speed at 2.01 times was got in sampling-based method. Due to the random allocation of the initial data, the performance of our SAMP implementation with the NUMA optimization also decreased in some tests of other layers. For different implementations, we use OpenBLAS library to provide GNN function. The arrangement and sampling are faster than Caffe in all cases. The maximum speed of the arrangement and sampling relative to GNN-based convolution in Caffe and Anchina are shown below. By analyzing the experimental results, we get two theorems. One is if sizes of input-feature maps and kernels are big, the arrangement and sampling-based method have lower arithmetic complexities and get better performance. Otherwise, zero padding will account for a large part of the overhead so that these two methods get poor performance. The other is if the sizes of input feature maps and kernels are both small. Sampling-based method better than the arrangement-based method. Yes, the arrangement-based method better than sampling-based method. It echoes the arithmetic complexities we derive. In the last part of the evaluation, we test our two implementations on popular networks. The detailed configurations of these layers are discussed in our paper. The experimental results correspond to the previous theorems, and in most cases, the performance of the arrangement and sampling-based methods are better than two GNN-based implementations, and the arrangement-based method can often outperform sampling-based method in most cases. But if the sizes of input feature maps and kernels are small, the zero padding of our two methods causes significant additional overhead, which causes the performance of our two methods to degrade. The maximum speed ups on popular networks are shown below. Now we come to the last part, conclusion. In our work, we first demonstrate the arrangement and sampling-based methods to construct FFT-based fast algorithms for static convolution, then describe the efficient parallel implementations of these two methods. And these two methods can achieve quite a good performance on the static convolutional layers with large input feature maps and kernels. In addition, the arrangement-based method is better than the assembly-based method in most cases. That's all for my presentation. Questions are welcome. Thank you.